Digital modulation schemes like two-tone AFSK are limited by the narrow bandwidth of FM transceivers. One way to increase data rate is by encoding multiple bits per symbol, which allows more data to be transmitted for a fixed bandwidth. In quadrature phase shifting, or QPSK, a fixed carrier is shifted by one of four phases, each representing 2 bits. To modulate QPSK, 2 quadrature carriers are amplitude modulated at the symbol rate. Adding the resulting signal yields a constant envelope sum with 4 possible phase shifts. To demodulate QPSK, we lock to the reference phase of the transmitted carrier using a PLL. Our PLL observes the zero crossing of the received signal's derivative using a polyphase filter bank. Using the recovered clock, we separate the signal back into its constituent components, classify them as zeros and ones, and form the original bit stream. Since the PLL can lock into any one of the 4 phases present in the received signal, we differentially encode our bit stream so that only changes in phase determine the outputs. To correct for magnitude and phase response of the audio passband, our receiver uses the constant modulus algorithm, a blind equalizer that works for constant envelope signals. Since frequency offsets and hardware accumulate as phase error, our demodulator uses a Costas loop to adjust the receiver's frequency to match what was transmitted. Our system achieves low errors under high SNR conditions up to 2000 baud. However, errors are still unavoidable. To handle errors, we split our data into fixed-size packets. Each packet starts with a preamble to help the receiver's correction loops converge, followed by an access code that is correlated for bit alignment. A sequence number and control code are prepended to each packet. Some are used to transmit metadata, others are used to signal requests for retransmission. Then, each packet is whitened with a pseudo-random bit sequence and protected with a CRC. When errors are detected, a packet is dropped and the receiver requests a retransmission when the channel is clear. Here, our system transmits an uncompressed image at 2000 baud. Our system is implemented in GNU Radio, an open-source framework for real-time signal processing. A threaded Python TNC moves data in and out of GNU Radio and handles the link-level protocol. To transmit an image, we applied several compression strategies and transmitted the best one. We used 3 compression modes: raw image data, black and white data, grayscale, and full color. The specific compression method for each method was determined for maximum PSNR and minimum byte size. All were compressed using LZMA and had variable downsampling. Raw image data was sent if the compressed image was small enough to fit within the allotted time to give infinite PSNR. Black and white was based on thresholding each pixel of a grayscaled version of the image, dropping from 24 bits to 1. Grayscale and full color were used for natural images. The DWT coefficients of the images are quantized to a variable number of bits and sent. In addition, we began development of a thumb drive-sized radio interface that combines the audio card, GPIO, and USB hub in one device. Altogether, our system enables us to transmit and receive compressed images at under 4,000 bits per second over conventional narrowband FM.